KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
Free bus for LKG to 8th standard.
Free, hygienic and nutritious food.
NEET, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
KURINJI Education Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
In continuation to the last class, in this class we are going to discuss 3 exercise problems, that is 16, 17 and 18. So here first we are going to discuss the 16th problem, right? You just concentrate to listen first problem, then we will go for solution. See here, a small pin fixed on a table top is viewed from above a distance of 50 centimeters, full stop. By what distance would the pin appear to be raised if it is viewed from the same point through a 15 centimeters thick glass slab held parallel to the table? So understanding the situation is most important thing here. I will repeat once again. A small pin fixed on a table top is viewed from above from a distance of 50 centimeters, right? By what distance would the pin appear to be raised if it is viewed from the same point through a 15 centimeters thick glass slab held parallel to the table? Held parallel to the table, right? So that is what. Here they have given refractive index of glass, and one more small question. Does the answer depend on the location of the slab? Does the answer depend on the location of the slab? That is the question. Okay, right. Now first we are going to discuss the first part of the problem. That is what, see here, by what distance would the pin appear to be raised if it is viewed from the same point through a 15 centimeters thick glass slab held parallel to the table, right? For example, here is the table and there is a small pin, means, so first he is saying from here, next also he is saying from here only, but through glass slab which is parallel to the table, right? So we have to find the distance where the pin appears to be raised, the distance how much the pin appears to be raised, that we have to calculate. Okay, right. See now, see the solution, the distance through which the pin appears to be raised, the formula you know, that is real thickness of the slab minus apparent thickness of the slab. Real thickness of the slab minus apparent thickness of the slab in terms of image, that is what we are seeing. So this apparent thickness of the slab, that is what, apparent thickness of the slab is equal to real thickness of the slab divided by refractive index. This is what, refractive index, right? You know the formula, that is what, mu is equal to a real thickness by apparent thickness, right? Then what is apparent thickness? Real thickness by mu. So that we are writing here. So it is what, real thickness of the slab minus real thickness of the slab divided by refractive index. For example, if it is T, it is also T, no? So T minus T by mu, that is equal to T into 1 minus 1 by mu. T into 1 minus 1 by mu. Then finally, already they have given, it is what, thickness of the slab will be 15 centimeters and refractive index of the glass is 1.5, right? So that we have to substitute these two values in this equation so that we can find the distance through which the pin appears to be raised. That is what D you can find. Okay. So D is equal to 15 into 1 minus 15 into 1 minus 1 by 1.5, right. So this is what you can take it as LCM, and then 1.5 minus 1 by 15, it will become 0.5, right. So 0.5 means 5 by 10, right, and here 15, right. So it is what 15, and this is what 5, and here it is 15 into 10. Okay. So anyhow, by completing this equation mathematically, you will get it as 5 centimeters, right. You will get it as 5 centimeters. Okay. The answer will be 5 centimeters. Okay. Right. It is 15, ma. It is 1.5, right. It is not 15. It is 15. It is 1.5. That's why I am saying you please do the mathematical process. It is also 1.5, right. So when it is 1.5, this is also 1.5, no. Then automatically here you will get it as 5 centimeters. Okay. Right. And one more very important thing, because at last he is asking, does the answer depend on location of the slab? That is the question. Okay. See here, the answer does not depend on the location of the slab, because if you see that is what the formula for distance through which the pin appears to be raised, it is what T minus T by mu, no. So what is the T? Thickness of the slab. What is mu? Refractive index, right. So it depends upon the thickness of the slab and refractive index of the glass. That is what. Okay. So it is independent of, it doesn't depend on the location of the slab. Location of the slab, that is the conclusion. Okay. Right. So it is about 16th problem. Now see the next problem, that is 17th problem. First I will read the problem. See, figure shows, right. So there is a figure. So the figure shows a cross section of a light pipe made of a glass fiber of refractive index 1.68. Full stop. The outer covering of the pipe is made of a material of refractive index 1.44. Full stop. What is the range of the angles of incident rays? What is the range of the angles of incident rays with the axis of the pipe for which total reflections inside the pipe take place as shown, right. What is the range of the angles of incident rays with the axis of the pipe for which total internal reflections, that is what total reflections inside the pipe take place as shown, right. So when we were in a discussion about the applications of total internal reflection, so I discussed to you one of the important application, which was optical fiber, right. This problem belongs to that application, that is what applications of total internal reflection, and the application is optical fiber. Okay. Right. Here, so he has given some information, that is what is the information. So this figure shows a cross section of a light pipe, right, made of glass fiber of refractive index 1.68. So it is what refractive index of glass fiber. Then the outer covering of the pipe is made of a material of refractive index 1.44. What is the range of the angles of the incident rays with the axis of the pipe for which total reflections inside the pipe takes place as shown? So it is what this we have to find, right. So this we have to find. Okay. So it is like a normal. So here the light is entering into the pipe, here the light is coming out of the pipe, right. So it is what axis of the pipe, and it is what the ray which enters into the optical fiber, and here it is going to refract. Okay. And then it is going to reflect, and it is going to reflect, and again it is going to reflect, again it is going to reflect, again it is going to refract. Okay. Right. So first you write the given things, that is what mu2 is equal to 1.68 and mu1 is equal to 1.44. Right. Now we can find out the relative refractive index, that is what mu2 by mu1. So mu2 by mu1 means, you know very well, mu is equal to 1 by sin c. 1 by sine c, right? So mu is equal to mu 2 by mu 1 is equal to 1 by sine c I dash, because that we are going to find. We can't conclude right now. That's why we put just like IC dash, sine IC dash. So anyhow it is also critical angle. IC is nothing but critical angle. Okay, right. Now it is what 1 by sine IC dash now. Mu is equal to 1 by sine c. If you want to find this as a subject, then sine IC dash is equal to mu 1 by mu 2. So what is mu 1? 1.44. What is mu 2? 1.68. That is equal to 0.8571. Sine IC dash is equal to 0.8571. That is what IC dash is equal to 59 degrees. IC dash is equal to 59 degrees. You know very well what is the critical angle. Critical angle is the angle of incidence, for which critical angle is the angle of incidence, right, for which light reflected back into the same medium. Okay, I want to say one more condition here, ma. When the angle of incidence is greater than the critical angle, then what will happen? Light reflects back into the same medium. It won't go outside of that medium, right? That is the condition, you know, right? When IC dash is equal to 59 degrees, when IC dash is equal to 59 degrees, what about that rest of the part of the problem? See here, the total internal reflection will occur if the angle I dash is greater than IC dash. That is, if I dash is greater than 59 degrees, when R is less than R maximum. So what is R maximum? R maximum is the 90 minus 59. That is what? 31 degrees. 31 degrees. Okay. So R maximum means here, that is what? Angle of refraction. Generally R means here angle of refraction. Okay. Right. So use the Snell's law. That is what? Mu is equal to sin I by sin R. So sin I maximum by sin R maximum is equal to 1.68. From this you can find sin maximum, sin I maximum, that is what? 1.68 into sin R maximum, that is equal to, this is what you can write it as 31 degrees, right? Because here we got it, no, R maximum is equal to 90 minus 59, because it is 90, no. So normal means, you know, normal means it is what? It makes 90 degrees. It is 90 degrees. Okay, right? And here also it is 90 degrees, right? So this is what? R maximum is 31 degrees. So that I maximum will be, I maximum, it is what? Sin I maximum, it is 0.8662. And from this, that is what? I maximum is equal to sin inverse of this value, that is what? 0.8662. Then you will get it as 60 degrees. I maximum as 60 degrees. Okay, right. So thus all incident rays which make angles in the range 0 is greater than I, is less than 60 degrees with the axis of the pipe. With the axis of the pipe will suffer total internal reflections in the pipe. Total internal reflections in the pipe. Okay, that is what we can conclude somewhat here only, but we are going for detailed discussion. Okay, so here it is about 17th problem. In 17th problem it is application of TIR, total internal reflection, and that is also very important application, which is optical fiber, right? So by knowing the refractive index of two different types of materials which we used in case of optical fiber, right? First we are going to find the critical angle. You know very well what is the relation between critical angle and a TIR, that is what? Total internal reflection, and a refractive index also. Refractive index also. Okay, that is what, right? So now we are going to discuss the next example problem, that is 18th problem. See here. Here in this 18th problem we have to answer for five things, right? You know, in one problem there are 2 and there are 3 and there are 4, 5 also, no? So in this problem there are 5 things. Okay, so these 5 things we are going to discuss clearly, right? So and moreover one important thing is here, actually this is the question and this is the question, and okay, and this is also the question, right? Okay, and this is the question ma, and this is okay, and this is the question and it is the answer, and it is the question and this is the answer, right? And then this is the question, this is the answer. Actually first I have to write the complete question, then I have to go for solution, but for sake of easy understanding, right? So for visualization point of view, there itself I am drawing, there itself I drew. Okay, that is what, see here. So 18th question, first answer the following questions, right? First read the question, listen the question carefully. I am reading every line of the question and solution. You please concentrate, because listening is very important, right? Almost a lot of ideas you are getting there itself. Okay, see here. You have learned that in 18th question, first thing is A. So in case of A, you see here, you have learned that plane and convex mirrors produce virtual images of objects. Are you agree or not? Yes, we agreed, because already we studied and we also experienced with ray diagrams, right? Next, can they produce real image under some circumstances, right? He is asking, can they produce real images under some circumstances? Explain. So if yes answer is also you have to explain, if no answer also you have to explain. Okay, right? So the answer is yes, right? When the answer is yes, when the object is virtual, right? When the object is virtual, right, then image will be real. Image will be real. Okay, so see this. Yes, a plane or convex mirror can produce a real image if the object is virtual. Okay, right? And the two pictures are here, ma. So you can call it as A and B, right? Otherwise, observe both the pictures. It is what about plane mirror, and it is what about convex mirror, right? It is a plane mirror and it is a convex mirror. You know, this is what a real image, and it is a virtual object, and these two are the converging rays. This is in case of plane mirror. In case of convex mirror, it is what a real object, and this is what a virtual object. Okay, it is a virtual object. Here it is what virtual object, but it is real image, right? It is not real object, it is real image, right? And afterwards, these two are the converging rays. Okay, so it is about plane mirror and it is about convex mirror. Okay, right? So if you observe these two pictures, we can say that if a plane or convex mirror is placed in the path of rays converging to a point, so these are the rays which are going to converge. So here, in the path of these two rays which are going to converge, we kept a plane mirror. Here, in the path of two rays which are going to converge, we kept a convex mirror, right? So what happened there if you keep a plane mirror and convex mirror in the path of converging rays? Okay, so what happened? The rays get reflected. To a point in front of the mirror. See here. Here the rays get reflected in front of the mirror. Here also the rays get reflected in front of the mirror. Okay. So when the rays get reflected in front of the mirror, so finally what we are seeing? Real image can be obtained on a screen. See, here also real image, here also real image, right? So actually if there is no plane mirror, these two light rays have to go like this and they have to meet some other point here. But because of keeping plane mirror, these will be reflected and the meeting at this point, their real image is formed. Here also, if there is no convex mirror, these two light rays will meet this point. But because of this convex mirror what we arranged, these rays will reflect and will form the image here. That is what real image. Okay. So this is the arrangement to get real image in case of plane mirror and convex mirror. But our general statement is, we are saying that in case of plane mirror and convex mirrors, we produce virtual images of objects, but we can also produce real image, right? So that is like this, okay ma? Right, next. See here, it is what B. See this. A virtual image, we always say cannot be caught on a screen. Yet, when we see a virtual image, we are obviously bringing it onto the screen of our eye. That is what retina. Is there any contradiction? So, while talking about the difference between real image and virtual image, we are saying that virtual images we can see only, we cannot caught on the screen. But real images you can catch on the screen. That is the statement we are giving, right? So, is there any contradiction? Why? Because in our daily life, when we observe when we see the object, right, what will happen? The image has to form on the retina, right? You know that. But here we are seeing the virtual image, but it is going to form on the retina. So, is there any contradiction? Right? Okay, that is the question, and the answer is no contradiction. Right? How can we satisfy? How can we say that there is no contradiction? See here. When the reflected and refracted rays are divergent, the image is virtual. Listen carefully. When the reflected and refracted rays are divergent, the image is virtual. Okay, right. These rays converged by the eye lens to form a real image on the retina. These rays, right? So these rays are converged by the eye lens which is present in our eye to form a real image on the retina, right? So the next thing is the virtual image serves as a virtual object. The virtual image serves as a virtual object, and the screen is not located at the position of virtual image, and also the screen is not located at the position of virtual image, so that there is no contradiction. There is no contradiction. I will repeat once again. When the reflected and refracted rays are divergent, the image is virtual. The image is virtual, right? So the rays converged by the eye lens to form a real image on the retina. So these reflected and refracted rays converged by the eye lens to form a real image on the retina. The virtual images serves as the virtual object. Also, the screen is not located at a position of virtual image. Based on this information, you can say that there is no contradiction. So you keep in mind, the reflected and refracted rays are divergent, then the image is virtual. Image is virtual, and these are the rays which are converged by the eye lens to form a real image on the retina. So this information is enough to understand the situation, right? Next, see here, see this ma. First see the question. A diver underwater, a diver who is going to give the diver. So a diver underwater looks obliquely at a fisherman standing on the bank of a lake. Would the fisherman look taller or shorter to the diver than what he actually is? So will he appear shorter or taller? You can see this picture. It is what fish? It is the eye of the fish. It is water medium. It is air medium. Fisherman, right? It is AB and AB dash. It is what PQ normals at these points, right? So it is the actual meeting, and it is what because of the illusion. Okay, right? So here, if the man looks taller to a diver underwater. Why? Because as the fisherman is in air, the light rays travel from rarer to denser medium. You know very well, when light is traveling from rarer to denser medium, it bends towards the normal, right? Towards the normal, and appears to come from a larger distance. So you can see that it is the actual height, but he is appearing like this, right? So that the man looks taller to a diver under water. Okay, so that is what the here. So AB is the real height, and AB dash is the apparent height of the man. height of the man. Okay. So here these points PQ are in fact close that the rays through these points can enter the smaller aperture, of the eye of the fish, but fish is underwater. Okay. So finally to this C, the answer is he appears as a taller. Because the light is entering from rarer to denser, it bends towards the normal and the rays appears to come from longer distance. That's all. Next D, see here. Does the apparent depth of a tank of water change? Does apparent depth of a tank of water change if viewed obliquely? If so, does the apparent depth increase or decrease? That is the question. Does the apparent depth of a tank of water change if viewed obliquely? If so, does the apparent depth increase or decrease? See here. If you see this picture, you can understand. You can easily understand, right? It is the observer position, it is also observer position. Here it is the normal viewing, it is oblique viewing, right? It is what real depth, it is the apparent depth here in case of straight viewing or normal viewing. It is what apparent depth in case of oblique viewing, right? So here the answer is yes. Yes, the apparent depth decreases for oblique viewing from its value of normal viewing, right? So that you can also see in the picture. See here, it is what H1 dash now. It is what H1 now. So here I have written small information, that is what H1 dash is less than H1. That is the answer. So if you see the picture, you can understood, right? Even no need of matter also, right? So for this, does the apparent depth of a tank of water change if viewed obliquely? Means the answer is yes. Yes, the apparent depth decreases for oblique viewing when compared to the normal viewing. That's all. Next, last one. See here, it is what E. The question is, the refractive index of a diamond is much greater than that of ordinary glass. That's, it is a fact. It is the statement. Is this fact of some use to a diamond cutter? Is it fact of some use to a diamond cutter? Okay. The answer is yes, it is a fact. It is a fact to a diamond cutter. But how? That is the answer. That we want to say. Okay, see here. Refractive index of a diamond is high. You know very well. It is what? 2.42. So its critical angle is small because the formula mu is equal to 1 by sin C. Mu is equal to 1 by sin C. It is what? 24 degrees. When mu is 2.42, critical angle is 24 degrees. Okay, right. A diamond cutter makes use of this large range of angle of incidence to ensure that light entering diamond suffers total internal reflection several times. Okay. So when light emerging out, it produces a sparkling effect. Okay. I will repeat once again, you please be concentrate. The answer is yes, no doubt. But we have to explain, no. That is what, very well, the refractive index of diamond material, that is what is high. When refractive index is high, critical angle is small. That is what? 24 degrees, right? So this diamond cutter makes use of this large range of angle of incidence. Why? Which helps us that the light entering diamond suffers total internal reflection several times. Then it gives or it produces a sparkling effect. Okay, right. So in this class, out of these three problems, the last problem is important for us because in this problem we are studying various reasons and various situations. Okay, so you please go through this 18th problem again and again, right? So the first problem we discussed based on that what the real depth and apparent depth. Okay, so based on that we found distance through which the pin appears to be raised. And the second problem is application of TIR, that is what? Optical fiber. And the third problem we discussed different situations and we have given reason for everything what he is asking, right? So please go through the 18th problem again and again and observe all this situation from your point of view, right? I am not saying to learn, I am saying to think from your point of view. Okay, right. Thank you. In the next class we are going to discuss next continuing problems. Thank you.